In this lecture, I will cover the data cleaning problem, the data quality problem and sources, and the data quality continuum, data gathering, delivery, storage, retrieval, mining, and analysis, constraints around data quality and data quality metrics, and data integration. Data cleaning helps to deal with missing data. For example, one sensor data set might have humidity while the other does not. Data cleaning also helps to deal with entity resolution. So for example, the difference between IBM versus international business machines. It also helps to deal with unit mismatch. For example, in one data set, you might have dollars, in another, you might have pounds, and so on. Now, the statistics view of how you deal with data that's dirty is that there's a process that produces data, and we want to model ideal samples from that process. But in practice, we have non-ideal samples. That's because of distortion. Some samples are corrupted by a process. Selection bias. The likelihood of a sample depends on its value. And left and right censorship, where we have users that come and go from our scrutiny. So sensors, for example, that enter our data set at some point and then leave our data set. And dependence. Samples that are supposed to be independent but are not. So for example, in social networks, individuals within a social network are not necessarily independent. So we can add models for each type of imperfection, but the challenge is we can't model everything. So we have to think about what's the best trade-off between accuracy and simplicity. From the database point of view, with dirty data is as follows. So I've got my hands on this data set. Some of the values are missing or corrupted or wrong or duplicated, but results are absolute because we have this relational model. And so we get a better answer by improving the quality of values in the data set. The domain expert's view of dirty data is that this data doesn't look right or this answer doesn't look right. So they want to understand what happened. And domain experts have an implicit model of the data that they can test against. A data scientist's view is some combination of all of the above when they're looking at dirty data. Where do data quality problems come from? Many places. For example, the source data could be dirty on its own, or transformations that you apply to the data could corrupt the data. And this is a challenge of the complexity of the software pipelines that we build to process data for data science. We can also have clean data sets that are screwed up because of the integration where we combine multiple data sets together and do that incorrectly. Things that are rare errors can become frequent errors after we perform a transformation or integration. And even a clean data set can suffer from bit rot. That's data that loses either its value or accuracy over time. Or any combination of the above can cause data quality problems. So again, looking at the big picture, where does dirty data come from? It can come from the extract, transform, and load process where we have to deal with integrating data from multiple different data sources such as application databases, files, and logs. We need to clean this data when we move it into our data warehouse. Let's look at a real-world example. Here's a graph of ages of students that are actually taking this course. On the x-axis, we have ages, and on the y-axis, we have a count of students. So what's wrong with this data? Well, if we look very closely, we'll see that we have 109 students that are under the age of 5, and we have 26 students that are over the age of 100. The problem here is that this data is based on self-reported ages. So if we were to just blindly import this data into an analytics pipeline and try to process it, we'd run into a number of significant problems and challenges. Here's another cautionary tale about data cleaning. This is a picture from the National Center for Atmospheric Research that shows the appearance of a hole in the ozone layer over Antarctica. Now, when this first occurred, it was observed in 1976, the scientists thought that their instruments were malfunctioning because they didn't expect to see it. And so they rejected the data as unreasonable as a part of their data quality control algorithms. But in reality, we know that that actually was a real hole in the atmosphere. There are many different types of dirty data problems that we can run into. For example, parsing the text from a text file into fields may have trouble because there are different issues with the separators. The naming conventions that we use can also cause problems with entity recognition. For example, abbreviating New York City as NYC. We may have missing information like a required field, for example, a key field that we're using for tabular data. We also may have violations of what's called the primary key in a database when we move from unstructured to structured data, or when we're trying to integrate additional data into our database. We may have licensing or privacy issues that prevent us from using data the way that we'd like to. We may have different representations for data. Some people may refer to the data as 2 numerically, or others written out as TWO. Fields may be too long and truncated during the integration process. We may have duplicate or redundant records that are exact matches or approximate matches for each other that we have to detect and remove. We also may have formatting issues. Formatting issues are particularly a problem when we're dealing with dates, as there are multiple different representations that we can use. Consider, for example, European versus American representations of dates. There are many meanings of data quality and many uses of data. We can use data for operations or for aggregate analysis or for customer relations. These are all very different ways of using the data with different requirements on data quality. There are also different interpretations that we may have for data based upon the quality of the data. If we don't understand all of the rules behind the data, it might actually be useless to have the data. And then there's a question of data suitability. Can we get the answer that we want from the available data? We may have proxy data that's approximating the data that we're looking at, or we may be missing the important relevant data that we need to make a decision. Data quality spans a continuum, and data and information are not static. Data flows in a data collection and usage process through multiple stages. We gather the data, we deliver the data, we store the data, perhaps for a very long time. We integrate together multiple different data sets. We retrieve data, and then we perform mining and analysis. We're going to go through each of these steps in this lecture. We begin with data gathering. How does the data actually enter the system? And this is part of the experimentation or observation or collection process. It can be a source of problems, including issues around manual entry of information versus automated data entry. It can be due to approximations or surrogates, maybe constraints in the software or constraints in the hardware. It can be due to a lack of uniform standards for content and formats. It can be due to parallel data entry. This causes duplicates, or it can be due to measurement or sensor errors. Some potential solutions to the data gathering problem are to be preemptive. Design a good process architecture that builds in integrity checks. Design good process management that rewards accurate data entry, sharing, and stewards. These are the people who are responsible for data entry. Also, consider being retrospective. The cleaning focus should focus on things like duplicate removal, or merging and purging bad information, or performing tasks like name and address matching, or field value standardization. Also think about a diagnostic focus, automating the detection of problems during the data gathering phase. Data quality issues can also be introduced during data delivery. For example, destroying, mutilating information through bad preprocessing. As examples, inappropriate aggregation or incorrectly converting null values into default values. It can also happen due to the loss of data, say from a buffer overflow or transmission problem, or a lack of integrity checks. Potential solutions to the data delivery problem are to build reliable transmission protocols. Use a relay server to store data and verify it before it's inserted into the data set. Use checksums or a verification parser for verification. Determine, does the uploaded file actually fit the expected pattern? Examine the relationships. These are the dependencies between data streams and preprocessing steps. And ask your data supplier to provide you with a commitment around the quality of data that they're providing. Data quality problems can be introduced during data storage. So you have a data set. What do you do with it? You store it. But there can be problems in the physical storage of that data. Now, this is a potential issue, but storage is cheap, and so we should store redundantly as an example. So some of the problems that we can run into in storage are logical. For example, having poor metadata. So when we have data feeds that are derived from programs or legacy sources, what does it mean? If we don't understand what the metadata is for these programs, we can't understand what the quality of the data is. Also, having an inappropriate data model is a problem if you don't have the right timestamps or the correct normalization of the data. Or if you make ad hoc modifications to the data, changing the structure, for example, to fit the graphical user interface that you use to explore the data. Or if you have hardware or software constraints. For example, transmitting the data via Excel spreadsheets, or running into Y2K, year 2000 problems because you chose to use 2-digit years instead of 4-digit years. Potential solutions are to make sure that you document and publish the data specifications. Track that metadata very carefully. Good planning can also help. Assume that everything bad will happen and then plan for it. This can be very difficult, however, to anticipate all the potential problems. Also consider using data exploration. Browse the data or use data mining tools to examine the data and make sure that it meets the specifications that you've assumed, or to determine has something changed that you didn't expect. Data quality problems can also arise during data retrieval. Exported data sets are often just a view of the actual data, and problems can occur because the source or the need for derived data was not properly understood. Or it can just be ordinary mistakes, for example, performing an inner join instead of an outer join, or not understanding what null values mean. There can also be computational constraints. For example, producing the full history might be too expensive, and so you supply a limited snapshot instead. But what are the limitations of that snapshot? Or it could be incompatibility issues. For example, producing the data in ASCII instead of Unicode or UTF-8. Data mining and analysis can also introduce problems. You need to understand what you're doing with the data, and there can be many problems that can occur during the analysis phase. Scale and performance issues, confidence bounds, understanding what they are, black boxes or dartboards, being attached to a model, having insufficient domain expertise, or applying casual empiricism, that is, using some arbitrary number to support a preconception. So for retrieval and mining, there are many potential solutions. For data exploration, you can try to determine which models and techniques are appropriate. Try to find data bugs and develop domain expertise. You should perform continuous analysis to determine are the results stable? If they change, how do they change? And it's very important to have accountability. Make analysis part of the feedback loop. Data quality constraints are a way of capturing many data quality problems. For example, we can use the schema's static constraints. Say, for example, nulls are not allowed, or specifying the field domains, or specifying constraints on foreign keys. But many other data quality problems are due to problems in the workflow. These we can capture with dynamic constraints. For example, saying that all orders above $200 are processed by biller number 2. Now, data quality constraints often follow an 80-20 rule, where a few constraints capture most cases, but we need thousands of constraints to capture the last few cases. Constraints are measurable, so maybe this is a way of getting towards data quality metrics. In terms of data quality metrics, we want a measurable quantity, something that indicates what is wrong and how we can improve. Now, the challenge here is that we have to realize that data quality is a messy problem and there's no set of numbers that's going to be perfect. But we want metrics that are directionally correct and improve as we use our data. Examples of types of metrics are static and dynamic constraints, or operational and diagnostic metrics. Now, there's a very large number of possible metrics that we could have. We want to choose the most important ones. So examples of data quality metrics that we could consider are conformance to schema. We can evaluate our constraints on a snapshot of our database. Or conformance to business rules. We can evaluate our constraints every time the database changes. Accuracy. We could either perform a very expensive inventory, or alternatively, we could track complaints. This is sort of a proxy metric. Another alternative is to periodically audit our data set and see if the samples match what we expect in terms of accuracy. There are other data quality metric issues like accessibility or interpretability. We can also have glitches in our analysis that we want to track, or we can have metrics around successful completion of the end-to-end process. You should use a multidisciplinary approach when attacking data quality problems because no one approach will solve all of the problems. As an example of some of the disciplines that you want to use, they include process management, ensuring that you have the proper procedures, statistics, focusing on analysis so that you can find and repair anomalies in the data, database management techniques, so you can focus on relationships to ensure consistency, and metadata and domain expertise. What does this data mean, or how do you interpret this data? Now, data quality issues can also be introduced during data integration, when you're combining data sets that you've acquired or have collected across departments. This is a very common source of problems because oftentimes you have heterogeneous data. There might not be a common key, or there may be different field formats. In this case, you may have to apply a technique called approximate matching. There may also be different definitions of what is a customer. In one data set, it may be an account. In another data set, it might be an individual. In a third data set, it might be a family. Time synchronization can also be a problem during data integration. Does the data relate to the same time periods, or are the time windows compatible? Another integration challenge is when you have legacy data that's coming from different spreadsheets in different formats, or files with ad hoc structures. A challenge that we have during data integration is duplicate record detection, or dedupe. Examples are resolving multiple different entries, identifying what is an appropriate entity or a matching entity, or determining which references are correct, or which object IDs should be consolidated, or removing duplicates by merging or purging values in the data set, or linking together records spanning across different data sources, or performing approximate matches, where we accept fuzziness instead of an exact match, or householding. This is a special case where we try to determine things like, are different people in the same household? Here's an example of entity resolution. These are two listings that we scraped from Google and from Amazon. Are these two listings the same product? They appear very similar. In fact, they are the same product. In the lab, you'll look at an algorithmic approach to doing entity resolution. Let's look at some more examples of data integration. So here's a dedupe example from Bing Shopping. And we can see we have two products here, Apple iPad 2s. And it turns out these are actually the same product, but they haven't been merged together when we see the list, even though they should actually be merged together. Another example is to take your data sets and convert the entries in the data sets into a canonical form. The example here is the U.S. Postal Service provides guidelines for canonicalizing mailing addresses. By converting a mailing address to a canonical form, we can try and determine whether two addresses are actually the same address. In general, we can apply very sophisticated techniques during the data integration process to detect duplicates or other problems. We can use evidence from multiple fields, both as positive examples that two things are identical or negative examples that they are separate. We can also use evidence from linkage patterns with other records, and we can apply clustering-based approaches. Again, there are more sophisticated techniques that we can apply here. But there are lots of additional problems that we can run into during the integration process. Are things stored as addresses or as number, street, and city? What are the units that are used? And how do we deal with merging together two data sets that have different units or differing constraints, both static and dynamic? Or how do we deal with the fact that there may be multiple versions that we're trying to combine, or a schema that may have changed over time, or dealing with other metadata in addition to the data that we're trying to merge? All of these are issues that we have to worry about. Now, in terms of solutions to the data integration problem, there are commercial tools based on a significant body of research in data integration. And there are many tools for dealing with problems such as address matching or schema mapping that you can use. There are also data browsing and exploration tools that you can use. These can help you identify the many hidden problems that may happen when you're trying to merge together or integrate in new data. You can also view the before and after results and see, did you get the intended results when you integrated in a new data set?